binomial coefficients, and we have this table of values, which is called Pascal Triangle. And I want to look for more patterns. There's lots of patterns to find. Let's see what we see, and we'll see where it takes us. So let me do this a little bit. So I'm going to start by I'll fill in a few more values. So if we believe that I claimed that you can always get each entry by adding up the one above it and the one above it to the left. So if that's true, which we haven't proved it, but if that's true, then that gives us a very easy way to fill it in without having to compute factorials and tangle stuff. Maybe we'll fill it in and then we'll just like compute one just to see that it actually matches up. And, you know. Okay, so this is going to be 1 plus 6 is 7. Switch back. 6 is 7. 6 plus 15 is 21. 2 plus 20 is 35. 29, 7. There. And here I'm going to get 8, 28, 56. Yeah. 35 plus 35 is 70. And then it's going to be symmetric, right? So it's going to put 56, 23, 8, 1. Let's do up to 10, just to be a nice number to stop at. So these are the ones here. And then let's see, 8 plus 28 is 36. 56 is 84. 126. Oh yeah, of course, right. 126 twice, whatever. Like something is not making sense. Okay. And then, okay, last row, it's going to be 45. It's going to be, let's see, 120. 10. So 210. It's going to be 252. Let's do, I don't know, just for fun, let's do like this one, just to double check. So this should be 10, choose 4. Right, and we know that's going to be 10 factorial divided by 4 factorial times 6 factorial.
And we did before.
What was that?
The one we did before. Perfect.
The one we did before? Oh, it is. The soup. You're right. I don't know, did we actually say what the answer was before? Maybe we did 210. That was totally not intentional. Maybe we should have pretended it was. So this is going to be 10, 9, 8, 7. This cancels with, 6. Let's put this here. These cancel. And then I got 4 times 3 times 2 times 1. And we did do this, didn't we? And then, 4 and 2 cancel to 8. 3 cancels to 3. 10 times 3 times 7. 210. Cool. So that seems to work. So I think what I want to do now is turn to a neighbor or two and just brainstorm some patterns that you see. And you can look at just to prime your thinking. Look at like even and odd things. Try adding up some things. Try, do you see relationships between numbers in different rows? We we've already talked about the fact that it's symmetric, but maybe there's other, anyway, just whatever you can think of. And then whatever you come up with, we'll brainstorm a list, and then some of them we can investigate further. So, off we go.
Third column, it goes on by one more every time. It will just equal. So, yeah, type this one out, you'll see that these are 5, 50, 21, 6.
Yeah, I know this is all. Because 7 choose 3 is the same as 7 choose 4, but by copying Pascal Triangle, we can add 15 and 20 to get 35, same with 20 and 15. Again, there's just 2 different ways to order things. 7 choose 3, you have a remainder of 4 with the amount of stuff you have left over, and 7 choose 4, you also take away 4. So it's 2 different ways of viewing how to choose stuff. So it's like symmetric. That's the same for the rest of the tree, like 7 choose 1 is just a different way of viewing 7 choose 6, because you're always just left with a different amount, but just on the other side. That's why the tree is symmetrical to a certain point. It's similar to n choose k is equal to n minus k. Yeah. Because if you order the factorials, at one point, if you have k and then n choose k, it's basically these two become this factor right here comes this factor, and this factor comes like that. That's why that's a symmetrical tree. I'm trying to think of one other property. Like we know that this itself is a tree, but also we can see that like hold on, like this.
Right. So I have lots of good conversation going on. So let's hear some ideas. It doesn't matter if you think it's simple or complicated or whatever. Anything that you noticed.
In the third column, each successive, I guess, output
talked about how it's symmetric, like if you kind of can draw a mirror, like it goes kind of like this, and it's the same on the left and right. So I think that's part of why we're finding these, those things are the same. Okay, cool, what else?
Also on column 2, or when k equals 2,
Yeah.
so I guess column 3.
We'll call it column 2. This is column 0.
Yeah.
This is column 1, column 2.
When n is odd, it's divisible by n, but when n is divisible by n minus 1.
Okay, so wait. Let's see. So you're saying in this column, when n is odd, the number here is divisible by n. So like 3 is divisible by 3, 10 is divisible by 5, 21 is divisible by 7, 36 is divisible by 9. Okay, but then the other ones, it's divisible by n minus 1. So like 6 is divisible by 4 minus 1, which is 3. 15 is divisible by 5. 28 is divisible by 7, and 45 is divisible by 9. Okay. How did you notice that? You're just, just looking for things like that are multiple, but yeah. That looks, I mean, that, we don't know if it continues. I know that it continues, but we don't. But that, so far, it looks like that is true. It's interesting. Anything else? Did anyone try like adding up any of the rows or columns or like anything?
Oh, well, I suppose, like, 1 and 10, you have to say that's, 11, and then in the very first column, adding all of that, that would be 11 as well. So maybe that mirrors as you go further
Wait,
back.
say that again? In the
So, second to last column, 1 plus 10 is 11, and then the very first column, that's 11 rows there. So, that would also be 11. I don't know if that happens continues inward, but.
So like this, you're saying this 1 plus 10, that's 11, and if I add up all these ones, I get 11? And you're asking, like, well, let's see, what's 1 plus 9 plus?
That'd be 55. And then, 0 plus 1 plus 2.
1 plus 9 plus 45 plus 55. And then if we add up all the numbers from 1 through 10, let's see, 1 plus 8 plus 6 plus 1 plus 5. And then, next one's gonna be 2 times 32.
Yeah.
With the sum, so like 64. Is it, someone add that in their head, is it 64? And also start using the, so, Disco has, binomial coefficients built in, so I can say things like 10 choose 4. So I could say, for example, if we want to add up this row, this is 6 choose k for a bunch of different k. So I could say, 6 choose k. I can't make a set. If I make it a set, then it's going to get rid of the duplicates, which I don't actually want. Right? So I can make it a list, which we haven't talked about, but if I add those all up, and if I do it with 7, I get 128. So what are these numbers? These green numbers here? Yeah, those are like powers of 2. So, you know, we might guess this is going to be 2 to the 8th. This is 2 to the 9th. 2 to the 10th. That does turn out to be true, and we'll think more about why, how we could prove that. But was there, Matthew, did you have your hand up earlier?
I figured I was asking about the pattern that we were just talking about.
Oh,
I figured
yeah.
out.
Yeah. Anything else? I'm just going to show you a couple cool patterns that I know about. And then we'll circle back and talk about some of these things that you all mentioned and see if we can figure out if they're true and why they're true. One interesting pattern that I'm not going to prove to you, but if you think about, so we just talked about adding up rows. What if you add up diagonals? So when I say diagonals, I mean like these diagonals. So, like, you know, this is 1, this one is 1, here's 2, 1 plus 2 is 3, 1 plus 3 plus 1 is 5, 1 plus 4 plus 3 is 8, 1 plus 5 plus 6 plus 1, 11, 12, 13. Those numbers look familiar? 6, 10, 4, that's 21, 21. Those look familiar? What are those called? Fibonacci numbers, right? Yeah. Yeah, so it turns out the sum of diagonals is Fibonacci numbers. What else? There's another cool thing that happens if you, let me see, how do I do this? I draw. So I'm gonna let's highlight all the odd numbers. Okay, and it turns out if you look at this, you know you see, okay, where are their odd numbers? You might not notice it's not anything simple like, oh, it alternates, right? Because like, for example, this row has all odd numbers, right? This row, it's like, well, this one's odd, kind of alternates, but this one has like an odd number here and there, but these aren't. It's not anything obvious if you just look at a row like it goes back and forth. But if you highlight all the odd numbers, you start to see a very nice pattern. Of course, 1 is always odd. 4, 6, 4, those are all be hard to see what's going on. If I did one more row, you can just take my word for it. It'll look like this. Oops. Get odds there. Like this. Anyway, we get this nice, like, if I zoom way out, maybe, I don't know. You get like these, what was that? Yeah, staircases. I'll do a couple more rows so you can start to see. It's like this fractal pattern of triangles. You get like bigger and bigger triangles with smaller triangles. I'm not calculating the numbers in my head, I just know what it's supposed to look like. And then we actually get like this row here, actually everything here is odd. Anyway, you get this pattern of like, there's like, oops, I don't want this square to get like a triangle here. Oh, it's still there's a big triangle here, little triangles here, and then there's like little, this is kind of like tiny triangles next to those triangles, and like a smaller triangle here. Anyway, it kind of ends up being this shape, where you get like, you know, a triangle inside the big triangle, then you like have smaller triangles in there, and you have smaller triangles in there. What's called known as the Sierpinski Triangle. It's actually not super hard to understand if you think about the fact that each thing is the sum of the one above it and the one above it to the left, and you know, like an odd plus an odd gives an even, an odd plus even is odd. So there's sort of a simple rule for determining if you know which ones are odd and even in one row, then you know which ones are going to be odd and even in the next row. It's kind of, all right. Anyway, that's just kind of fun. But let's come back and think about. Well, let's first think about the rows. So the claim is that if I add up everything in one row, so that's like you know, n0 plus n1, n choose 1 plus n choose 2 plus dot 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 plus n choose n is equal to 2 to the n. That's the claim. So we could probably prove that using the formula for n choose k and probably using some kind of induction. We could do it, it would just be a lot of algebra, and we do a proof by induction, and it wouldn't really give us that much insight into what's going on. There's a much nicer way that we can understand why this is true. If we think about what this means. So remember that n choose 2 means how many subsets of size 2 are there? If I have a set of size n, how many different size 2 subsets can I pick out of it? Right? Does anyone remember, if I have a set of size n, how many total subsets are there of that set? Of any size? Here. What was that?
Just one.
Oh, sorry, yeah, I misspoke. Yes, the only subset that's everything is there's one. But I mean how many subsets are there in total? subsets are there of that set? What do you mean?
Factorial?
No, n factorial is the number of ways to put them in a specific order.
Oh, yeah,
right?
to the end.
Yeah, it's to the n. We've seen this a couple times. So we saw this when we first were talking about sets and subsets. Right, like one way to understand it is you say, well, each thing in my set can either be in my subset or out of my subset. So for each thing I have two choices. Do I include it or not? And so the total number of choices I have is 2 times 2 times 2 times 2 times 2 to the end. Right, or we could think about, I can make a binary number for each subset. It's like 1, 0, 1, 1, 0 means I have this thing, I don't have this thing, I have this thing, I have this thing. There's 2 to the end of those. Okay, so this 2 to the n here is the total number of subsets, right, of a set of size n. And what do these things mean over here, the sum? Well, remember, like, n choose 2 means the number of subsets of size 2. N choose 1 is the number of subsets of size 1. N choose 5 is the number of subsets of size 5. So do you all see how, like, every possible subset is accounted for once on both sides of the equation? Right? This side is just all of them all together. And this side, we're counting them by size. So we're like splitting them out into sizes separately and say, okay, first I want to count all the ones of size 0, all the ones of size 1, all the ones of size 2. Right? But every subset has some size. I look at a subset, maybe it has size 3. So that got counted with n choose 3, and it didn't show up anywhere else. So this is like subsets of size 0, which is only one of those. Subsets of size 1, of size 2, etc. Okay, so that, and this is pretty typical in combinatorics, where you maybe could prove something algebraically, but it's much nicer to say, I have this equation. I'm just gonna explain why the two sides of the equation are just two different ways of looking at counting the same thing. And if I can show that both sides can be thought of as the size of some set, the number of some thing, then they must be equal. So actually, while we're on that subject, let's think about this one. So, right, this is saying, so n choose k, n minus 1, if I decrease n but I keep k the same, that means I'm going up. Right? And if I decrease both of them, it means I'm going up and to the left. Okay? So this is just saying, the value in each cell is equal to the sum of the thing above it and the thing above it to the left. Again, we could definitely prove this using algebra. We could just, substitute the definitions of these with some factorials and stuff, and we could, factor stuff and whatever. It wouldn't even need induction because it's not involving like a big sum of something like this. It's just, we could just do it. But there is also a combinatorial proof where we just say, no, we can see why these have to be the same because they're both counting the same thing, just in different ways. Okay, so we know what this side means. This side is just the number of ways to pick k things out of n, the number of subsets of size k. Let me see if I can convince you that this side is the same thing. So I have my set of n things, and let's just pick one of them, and we'll focus on that one. So maybe if I have all my soups, and I want to know the number of ways to pick 4 of my soups, and you say, well, let's think about chicken noodle. Okay, any way to pick 4 of my soups, either it's going to have chicken noodle in it, either I'm going to choose chicken noodle or not. right? And so I can kind of split it into those two cases. Say, first, let's see, how many ways are there to choose 4 soups if I definitely include chicken noodle? And how many ways are there to pick 4 if I don't include chicken noodle? Okay. Well, if I don't choose chicken noodle, basically what I'm saying is I still need to pick 4 soups, but I'm not going to let myself choose chicken noodle, so I only have 9 left to choose from. So now I'm thinking about what's the number of ways to pick 4 things out of 9 instead of 4 things out of 10. Right? So that's this here. This is saying this is the number of ways to pick k things out of n minus 1. So if there's one thing I don't let myself use, I only have n minus 1 things left, and I still have to pick k out of it. Or I say, okay, well, what if I definitely do choose chicken noodle? Now I've got 1, and I only need 3 more, and I have to pick those 3 out of the 9 that are left. And in general, right, if I do use that one thing, then I have n minus 1 things left, and I only need to pick k minus 1 of the remaining things to fill out my set of things. So that's an argument that this is always true, because we can pick a specific thing and say, well, let's split it into the 2 cases where I definitely use that thing or I definitely don't. Cool. Any questions about that so far? Okay. Let's talk about this this column 2. So I think it was Adam that mentioned, right? This column 2 looks interesting because it's going up. I think it goes up by 2 here, and it goes up by 3, and it goes up by 4, by 5. And the numbers in this column turn out to be they're important and interesting numbers. So how I want to introduce this. So if I'm going to write down a set, and I'm going to think about how many things are in this set. Okay. So I want the set of pairs x, y, such that x is in 1 to n, and y 1 to x. So for example, when n equals 2, I get well, x could be 1, in which case y could only be 1, because y goes from 1 up to x, whatever x is. So I could get 1 comma 1, right? Or x could be 2. If x is 2, then y is taken from the set 1 to 2. So y could be 1 or it could be 2. So I could get 2 comma 1 or 2 comma 2. Does that make sense? So for each x, I'm going to get a pair, all the pairs where the second number is like anything from 1 up to so like when n is 3, well, x could be 1 again, which means y has to be 1. X could be 2, which means y, so it's the same elements as before. But now x could be 3, in which case y now comes from the set, 1, 2, 3. So I could have 3, 1, I could have 3, 2, I could have 3, 3. And just for kicks, we'll put in n equals 1 because why not? There's only one thing here. So my question is, how big is this set? So in this case, there's one thing in this set. This has size 3. 1, 2, 3, 4, 5, 6. This has size 6. How big do you think the next one's going to be? 10. What was that?
10.
10? Why do you say 10?
Because it's following that pattern.
Yeah, it's following the same pattern, right? So the next, I'm not going to write out all of them, right? But it's going to be size 10.
So I mean, which makes sense.
Yeah, why?
It's a set of 2.
So what was that?
It's a set of 2 variables, x and y.
Uh-huh.
And the column itself is a column, driving from 2.
Oh, okay. Yeah, so maybe there's a connection between the fact that there's 2 variables and it's the column 2.
Yeah.
You're right, actually. There is a connection there. I can't even see, like, specifically why is the size so, like, to go from this set to this set, I add 2 things, and then to go up here, I add 3 things, and then I add 4 things. Like, why would that be the case? So this is like plus 2. This is plus 3. This is going to be plus 4.
Okay. Because I see the map, I can't explain it.
Okay.
I guess because it goes up by that new number every time. So with n equals 2, well, you have 2 now, so you have 2 more entries that account for both the previous number and current number. I don't know if that is revelatory or anything, but
Yeah. I think you're right. And you notice how, like, we always get the same elements as before, but there's just some new elements added on, right? So, like, in this case, when I go from 2 to 3, the elements I add on are 3, 1, 3, 2, and 3, 3. Right, so I'm always going to get, the new elements are where the first element of the pair is n, and then the second element can be anything from 1 up to n, so there's going to be n of them. Right, so maybe that's one way to understand it. There's another, we could also think of this in terms of programming. If you have something like, if you know Python, or it doesn't really matter if you don't, but if you have like a for loop where you say for x in, I guess in Python it would be like, well, this is pseudo Python. You can't write it that way in Python, but imagine you could. And you could just say like a nested loop that says for y in 1 to x, brings star. And the question is like how many stars get printed out. Right? It's going to follow the same pattern. This pattern happens a lot in programming. Anytime that, like, imagine, for example, that you have a list, and every time through the loop, you go through the whole list, and then you add something to the end of the list. That's a pretty common pattern, actually. And so the first time through the loop, it takes one operation because you just go through the list, and there's one thing in it. Then you add something to the list, and the next time through the loop, you have to go, it takes 2. There's 2 things in the list, so you go through both. Then you add something to the list. The next time, you have to go through 3 things in the list, right? So every time through the loop, the number of operations you have to do is going up by 1. Right? So it's like 1, and then you do 2, and then you do 3. So here's another way to envision this. So here's 1. In the second row, I'm just going to make like a triangle of dots. In the second row, I have 2 dots. I have 3 dots. Right, so there's like, this is 1 dot. This is 3 dots. This is 6 dots. This is 10 dots. So on. Right, so these numbers, 1, 3, 6, 10, 15, these are called the triangular numbers. Because, it's the number of dots in a triangle. That's one way to think of them, like as in this picture here. And, I hope that I've at least hand-waved that you're maybe not fully convinced, but you at least believe me that these actually show up a lot in programming. This kind of pattern, you often end up writing some kind of loops, or nested loops, where the number of loops that you're doing follows this pattern. And apparently, because those numbers show up here in this column 2, apparently, the nth triangular number is equal to, n choose 2, because that's all the things in that column are, that column 2 is whatever choose 2, so, that turns out to be true. Why is that? One way we can understand that, well, and actually, while we're on it, n choose 2 is really, it's n factorial over 2 factorial, n minus 2 factorial, which is equal to n times n minus 1. I guess actually it's like, maybe it's n plus 1 choose 2. But I don't know. It depends where exactly how we count it. So right, everything past n minus 1 in the n factorial cancels with the n minus 2 factorial. We just have n times n minus 1, and then we just get 2 times 1. So that actually gives us a formula for the triangular numbers. And if you think about that formula, actually that proves, I think, the thing that Matthew observed about like when these are divisible by n. Because here's your n and your n minus 1 showing up. You said sometimes it's divisible by n and sometimes by n minus 1. And depending on which one is even and which one is odd, the 2 will cancel with that one. The one that's even, and you'll be left with something divisible by the other one. I think, yeah, we'll stop there. There's different ways to understand why, why adding up the number of dots in a triangle, what that has to do with choosing 2 things out of a set of n. But I'll let you think about it. There's probably a lot of different ways to understand that, and it's more fun to see if we can figure out a way to make those things. All right.